You guys, get your Z-score charts out for a minute here. Hopefully you got those. There's a couple of skills you have to put together to be able to do chapter 8 and to understand what it's all about. And they're old skills. We're just kind of putting a few things together. Let me see. See if I have a marker that's going to work. So one kind of skill is this. If I know I have a normal distribution and the mean is, let's say, 52, and the standard deviation is 4.5. Can you figure out what's the x of z of 1.81? Okay, that's one kind of skill. So try to do this. You have a normal distribution. The mean is this. Standard deviation is this. What's the x score for a z of 1.81? And then secondly, that's the other skill we need to have. Both things I could have asked on this last test. We're just going to kind of combine these together. You need the Z-score chart for number 2, not for number 1. Hopefully it is. What formula are you guys using for the first one? Is anybody doing anything for the first one? You're like, we're just drawing ducks, man. We're just making it look like we're doing something. You don't really want to use this version of the formula because I know the z-score. You'd rather use the other one that, yeah. Whatever it is. What's the definition of a z-score? Yeah, z-score is a number of means multiply, standard deviations, the number of standard deviations from the mean to the data point. That's, that's that formula that's actually a note. Because every formula can be read as an English sentence because it's just a different language. Translate it into English. Now I just got to plug and chuck stuff. Right? To figure out the data point, well, how far is the data point from the mean? 1.81. It's 1.81 of these from the mean. And then you can figure out what that is. It's like 60.1. It's a little more than 60.1. 60.1. What is it? 145? Yeah. And you're like, whatever, math boy. All right. It's my one skill. Now, is everybody decent with this? I mean, this is old news by this point. Right? This is really old news. I could get the idea of this. The idea of a z-score is kind of silly. If I said M tells me how many chunks of 10 miles away I am from something, and M is 2, then I'm 20 miles away from something. And it's the same kind of idea. Z-score is the number of these from the mean to the data point. So that's why that formula makes complete sense. And it really is algebraically just resolving this for x. Now, how do I do number 2? What should I start off doing? So for a normal distribution, So what does that mean, bound the middle 80%? Can you guys, what would that look like if you drew it? The middle 80%. So the middle, yeah, you want to cut off compounding. That's the middle 80% right there. And I want to know these z-scores, that from the lines you just drew, those are z-scores, right? Those are z-scores. But I can't find a z-score from the chart unless I know an area that is below it. Now, do you guys all agree I want the z-score? That's going to be part of this answer, right? But the chart doesn't understand the 0.8, doesn't understand it. I've got to, what's the area that's below that z-score that I want? What area is here? If there's 80% inside, there's how much outside? 20%, so there's how much on this side? 10%. The book calls, gives this, let me give this to you right now because it's going to become big pretty soon. They use the Greek letter alpha. That's like the Greek A. Alpha in this case would be 0.2. Alpha is always the amount outside, the amount in the tail or tails. And confidence intervals always create two tails. Do you guys see that? If I cut it like this, chop, I just made two tails. So then the book likes to use alpha over 2. Why does that alpha over 2 make sense? Because what am I always going to do for confidence? I'm going to cut it in half to get that other side. Now, if you look at 0.10, what z-score do you get? What's the closest you can get to 0.10? Say again? Yeah, I get like 0.1003. That's the closest I can get to 10%. You guys agree? No? Please don't be looking at 0.01. That's 1%. So 0.10, the closest I can see is 0.1003. And what z-score is that? Yeah, well, negative 1.28. Negative 1.28. So this would be what? Positive 1.28. Because it's got to be bounding the middle, and normal distributions are symmetric. That's beautiful. So whatever this side is, that's the positive. Yes? Sweet. All right, now, what we do then is, if I did a couple things that could make this into a Chapter 8 kind of problem. Number one, I'd have to take a sample to get a mean. So here, the reason this is not a Chapter 8 problem is because I know the mean. Chapter 8 says, why don't we use this idea, but in a situation where I don't know what the mean is? Which is what situation? Almost every frickin' situation we're in when we're studying something. Right? We go to some town in Tennessee and we're like, we don't know how the average weight is, but we take a sample, we get X bar. That's our best guess. Right? So what do? We use this formula, we really do. We use this. But instead of mu, I've got to take a sample and then get an X bar. So the minute I take a sample, what's got to happen to him? He's got to change. I take a sample of size n, he's got to change. And then I use this idea. So if I wanted to be 80% confident, I would go up and down this many z-scores, this many standard deviations. So it'd be up and down that many. So it's kind of improving on our guess. Our guess is X bar, and we go up and down somewhat, a little bit, to say, I'm going to improve on that guess a little bit. I'm 80% sure that this interval would contain that mean, whatever it is. All right, now let's do a concrete example, right? Because this is the idea of it. Let's do a concrete example. So say we take a sample of 36 grades. And get we know sigma. So these are like grades from a course that's been running forever. So we already know what sigma is. We already know what the standard deviation is because we got tons of data already about that. So we take a sample at 36 grades. So we already know the standard deviation of these grades is 13.9. So how, this is a weird question because it sounds like I want an exact answer, but how likely is it that that's the actual mu? That's the real population mean? How likely is it that this exactly is the real mean? Very unlikely, right? It's possible, but I put a lot of money on it not being. So if I took 13 people in here right now and got your average age, I put a lot of money on it being not the real average age of everybody in the room. Should it be close? If it's a truly random sample, it should be close. So this plus or minus thing gives me an idea of like closeness in a way. So if I want to find the 98% confidence interval for the true mean grade. And when I say true, I mean population, right? Population mean grade. I just use the word true, just, I don't know why really, just because. So how am I going to do this? Well, I want a confidence interval. We're going to learn 2 more types of confidence intervals, but they all look the same. It's something plus or minus z something. Confidence interval's got to have an upper bound and a lower bound. So it's going to have that plus or minus in it. What I'm trying to tell you is I want you to understand a confidence interval. But if you have a test problem and it says find the confidence interval, find the 80%, 92%, whatever, you know you're going to use a formula that's got a freaking plus and minus in it. That's how you make an interval. So at least you can tell what section of your formula sheet to look at, right? Here I'm going to probably use the only one we know yet. And now I just got to plug everything in. The only thing that I am not given in this problem for the formula is what? Did they give me X bar? Yes. Did they give me sigma? Yes. Did they give me n? Yes. They didn't give me z, but they gave me a way to find it. So can you guys take a minute and figure out what that z-score is I'm going to use? The same way we just did with 80% a minute ago. It's the same exact idea. How do I know this is normal, by the way? Yeah, 36 is bigger than 30. So I know that if I graphed all the means, they would come out normally distributed. So try to figure out what that z-score would be for 98%. Oy, oy, oy. Probably the way we did that 80% one earlier. Because it's the exact same idea. So if you're not drawing the picture for yourself, you might be having a harder time than you should be. Some of you guys that remember that little baby chart that gives you, I don't know, remember I pointed out 90%, 95%, 99%. 98's not on there, haha.
You got a calculator today?
Yep. Need to borrow a calculator?
Thank you.
Sure. So what are you guys getting for the z-score? Yeah, the closest I can get to, well, 98%. All right, if we draw that out, the middle 98% is what it means. So how much is outside? If there's 98% inside, there must be 2% outside, so there must be 1% over there. So if I look up 0.01, I'll find this z-score.
-2.33.
Yes, negative 2.33. Make sure you see that. Make sure right now you see why the hell I put negative 233 there. So 0.01, the closest I can get to 0.01 is pretty close. 0.0099. That's closer than 0.0102, so we use 2.33. So what's this other one going to be? Yes?
-2.33.
So,
That's -8 -21 -5. And then
oh, it's trying. This system is initializing. Don't look at it yet. You might be concerned about you. There it is. Now it's focused.
I see that.
So the closest I can get to 0.01. There's 0.01s, right? See those 0.01s? The closest I can get to 0.0100 is right there. That's a little further away. So negative 2.33. If you use negative 2.325, I'm fine with that. But don't if you don't want to. I love the look on it. I'm like, if you don't want to, then don't do that shit. Just take the one that's closest. All right, good.
Oh, okay.
For a minute, like you're still angry at me. I'm like, I don't know what to do. So is that cool? So you can find any confidence level I ask. You just draw it, and then figure out, one side. Now, what's this guy got to be?
Positive 2.
Positive 233. Why? Because his normal curve is symmetric. Oh, really? Now, I only have one place for a z-score. Where's that idea of negative and positive? Well, obviously, it's right here. All right? So don't put like a negative z-score. It doesn't make any sense. The plus and minus is already in the formula. You just care about what the number is. It's 233. And now you can just plug and chug. All right? So if you plug in, I know the mean, 75.2. Give or take, 2.33 of these. 13.9 divided by the square root of 36. And I suggest you do the error first.
.398.
Yeah, I was getting something close to that. 5.398. You guys getting the same thing for this? This is the error piece, right? That's how much you're off by. Why does it make sense? Give or take. It's this. Give or take. This is how much I think I'm off by. 5 point. Say it again. I'm sorry.
398.
398. And then I just subtract that from this, add it to this. So if I subtract that from this, I get like 69.8, roughly. Is that right? If I add it to this, I get 80.6 almost. Is that cool? You guys get the same thing? All right.
We got 5.405.
5.405?
Yeah.
All right, let's see. Did you use 233 or 23? Yeah. Ooh, dissension. I like it. Yes, ma'am.
So the answer will always be in parentheses divided by a comma?
Hold on. The answer will always be in the form of a little sentence. Yeah. The interval, this is the interval, and then the real answer is interpreting what the interval means. Aw. So let's see, 2.33 times 13.9 divided by 6. I get 5.398.
Okay.
So then how do I interpret this? How do I write my little statement at the end? How does it start? Yes, we are 98% confident.
At the interval.
Good. That the interval
69.8.
69.8, 80.6 contains the
True mean weight.
true mean grade. I didn't really give more information than that, but If somebody else took another sample of 36 grades, would they get the same stuff here? Would they get the same thing? Could they? Sure. What's more likely? No. They'll get something different because they'll take a different sample. It'll be a little bit off. So will their interval be the same as mine? No. So if I had 100 people take 36 grades and make their own intervals, 98% of them, on average, would actually have the real mean in there. So only 2%, 2 of them would not. That's how to interpret this probability here. This is we're 98% confident because there's a 98% chance that our interval catches it. The actual nuts and bolts of this is pretty straightforward. The Z-score work we've done before. We're just now marrying it with some other ideas that we just kind of cobbled together. All the ideas in this are old. This thing is just putting all that stuff together. I like it. So whenever you see, today we're going to talk about percentages. So we're going to find, like, if I get a sample percentage of 40%, give or take 4% or something, that's what you always see. When you see like a poll or something at the bottom, they say plus or minus 4%. They didn't just make that up to cover their ass. They actually calculated it to cover their ass. Right? Okay. So let's see if we can't step into the other side of this handout. I'm going to start off with deriving the formula, as I always do. Isn't crazy? You guys all got this here? Okay. I want to remind you, the way we derived that formula we just used, we started here. I'm going to write that weird little symbol there. X is approximated by this. So what we did a minute ago was we said, well, if I don't have that, I have the next best thing and so forth, right? And then I have to change this and so forth. Okay. If I'm working with percentages, so for example, the beginning of a problem that we're about to get into for section 8.3, and real quick, the reason I skip 8.2 is because it uses a whole different chart. 8.3 still uses our Z-score chart, so I don't know why books don't just do it in the order I did, but who knows? So if I have, so the beginning of a problem looked like we talked to 80 people, and 13 of them like, coffee ice cream. Blah, 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 right? Can somebody figure out a percentage from that? What percentage would you get from that sample? Ooh, there's all kinds of stuff over here. Do you work? Yes. Thank God. What would the percentage be from the sample that liked coffee ice cream?
16.
How'd you do that? 13 out of 80, right? That would be the percentage and so forth. Now, so what does this mean? And what's the symbol for 80? What's 80? What's the symbol for 80? Well, 80 is the number of people we talk to, so that would be N. So there's an N, there's a P, there's going to be a Q for the people that don't like coffee ice cream. Do you see how this feels like a binomial? It's an NPQ problem. When we did binomial problems, so the classic one I always start with was 11% of all Americans are left-handed, right? Is that a parameter or a statistic? Just to bring something back to really torture you. 11% of all Americans are left-handed. Is that a parameter or a statistic? All Americans. Did I take a sample of Americans? I said all Americans.
You said a number, that's what
I said 11%. I don't care about what does a parameter mean? A numerical description of a population. 11% of all Americans. Oh, I'm describing all population. I'm describing a population, so that's got to be a parameter. When I have a mean, that's a parameter. What symbol do we use? So that would be the mean of the parameter is describing the entire population. So what symbol do I use for the mean of a population? What symbol do I use? I love you guys. Mu. For a sample, I use the symbol X bar. I like it. You guys with me? And like I said earlier, at least at the beginning, population has Greek letters, samples have our letters. Now we're going to kind of go away from that a little bit. We use the symbol P to represent like that 11% of all Americans. So that P symbol is like the mu. The P symbol is if it's the whole population. Is this the whole population? No. We talked to 80 people. No, that's a sample of something, right? So I can't use that letter P. You're going to love this shit. You're going to love this. This is sounds like the thing you don't want to wear. We use the symbol is P hat. The P hat, yes. Right. Now, no matter what clothing your P and Q are wearing, they still have to add to be 1. So what did you guys say this P hat was?
16.45.
Point. Say him 1625? 1625. So what would Q hat be? Point 837. 1 minus that, right? Just because they're wearing hats doesn't mean they don't add up to 1 anymore. What does the hat mean? They came from a sample. I like it. Just like mu means it's the population, X bar means sample. Sigma, population, S, sample. P hat, same idea. All right, I like it. All right, now watch. Now this gets interesting. Now, what's the formula for the mean of NPQ problem? NP. And for the standard deviation? Square root of NPQ. I like it. Now, in the same way that we divide by the square root of n when we take a sample and so forth, now I want X bar for the, so I'm going to be n times P hat. Is that cool? N times P is the population mean, n times P hat is the sample mean. Okay, I like it. And then my new standard deviation is going to be the square root of n P hat Q hat. All right. So just go with me for So the only new thing I've introduced is that P hat guy, but it's just like an X bar. It means it came from a sample. So I'm going to do the exact same thing we did before. I'm going to replace these with what I've got, the next best thing. So I'm trying to get a feel for the mean, right? And the mean would be NP. And that's approximated by, what am I going to use? I don't know the mean. So what's the next best thing I can use? NP hat. That's the sample mean. That's the next best thing I can use. I am right now constructing a formula that you guys are going to use. You are not going to have to construct it every time you do a problem. I always love the looks in the faces. I want to show you where the formula comes from, and then you're going to use it, right? So what's the next best thing I have for the mean is NP hat. Plus or minus Z, and what's the standard deviation going to become now? Square root of NP hat Q hat. So again, just like I had before where I had mu plus Z sigma, and I put here X bar, and that means I put here sigma over square root of n, right? Is that cool? The same idea, I kind of replaced it. This was my best guess, and that had to change here. That's my best guess for the mean, and that's the standard deviation of that sample. Now, is it still not good enough? Because I don't give a shit about the means. I want to be able to say 40%, give or take 4%, like I just said a minute ago. I want just percentages. So what do I have to do to both sides to get just the percentage by itself? What do I want to divide away? What do I not want there? I want a percentage plus or minus something, not n percentage plus or minus something. So I probably want to get rid of the n. So my percentage, my population percentage, is approximated by P hat. Now here comes some algebra. Oh, that's sneaky algebra. So freaking important to know freaking algebra. Can I just cancel these? No, why not? That one's in a radical, that one ain't. So they don't have the same radical. You can only combine things by multiplication division if they have the same root. Fundamental algebraic idea. N is equal to the square root of what? N is equal to the square root of what? I love you guys. 5 is equal to the square root of what? 5 equals the square root of what? 25. What'd you do to 5 to get 25? You squared it, of course, because what's the square root going to do? Undo that. So n is equal to the square root of n squared. Why am I doing that shit? Because now they both have a square root. Now I'm allowed to do something between the two of them. Unfortunately for me, they don't cancel, but at least I could do something. What happens here? Yeah, one of the n's dies. So I end up with p hat plus or minus. I don't want to write two radicals. I'm going to write one big-ass radical. So that's my next equation. This is the formula for a confidence interval for a percentage. So it's an example, and then I'll unleash you on this handout. So an example, nice concrete example. Let's do the example I've already got up here as I erase it. Shit. We talked to 80 people, and 13 of them like coffee ice cream. Create the, let's make it a 99% confidence interval. I'll tell you this, I'm going to talk in a minute. Well, let me see what order I want is. You guys have what you want from here, right? Okay. There was a while back. What should you be concerned about here that I made a point of in the last problem? Why do I know I can do any work at all? What do I need to know that I can do any work at all with this? Because what do I want to do with this first thing? Get a z-score. What's the only time I can use that chart to convert between percentages and z-scores? If I know it's a normal distribution. Do we have a way of gauging that here? We don't. N greater than 30 is not good enough because that works for means. That's the central limit theorem as it approaches the mean. And this is stuff about percentages. Shit. So I can't use N greater than 30 when I have NPQ problem. Stay with me. So hopefully some of you guys see. We're going to do this. Let's go ahead and do this. I think I'll do this in this order. We'll do this, and then we'll talk about what it takes for it to be normal, and I'll show you that this was normal. So let's do it like it's normal, and then we'll see how to figure out that it's normal. So trust me, this is normally distributed. We just don't know how to check that yet. Do I have everything I need? We already figured out p hat from earlier, right? It was 1625? Was it? So that meant q hat 0.8375. 99% confidence. Can you guys, what's the z-score I want to use? It's going to be an asterisk, dude. Or you can use the little baby chart for this one. 2.575. I like it. So the z I want is 2.575. That comes from this 99% confidence. And if you forgot about the baby chart, you would do 99% in there. How much is outside then? 1%. How much is on one side? 0.5%. Look up 0.005. It would be a little asterisk. You follow it. 2.575. Bam. And what was n? 80. So I got everything I need for the formula now. So this, my best guess for the actual percentage, the P, the population percentage, is this guy. So let me see. Let me stop right here. This part is old news. You got to be able to do that from the other confidence intervals anyway. This one is from the problem. This is just calculating the percentage we see in the sample. So nothing up here is anything new either. Each piece of this is old stuff. The only new thing is putting it together to tell us something. So this is 0.1625, give or take 2.575 of these. Got it. Square root of 0.1625 times 0.8375 divided by 80. Now the big mistake people make is they don't put this in the calculator correctly, and it all goes to shit. So what's the first piece of that I highly recommend you figure out? Aw, poor little dude. Yeah, the error. There we go. Is that going to help you? No. All right, there we go. All right. So if I try to do just that error piece, it would be 2.575 times. Now if you have an older calculator that opens a parenthesis here, do not close it until you get everything you want in the square root. Closing the parenthesis means you're outside of the square root. How much of the formula after this do I want in the square root? All of it. If you have the newer calculator, the square root symbol just gets bigger, which is really, really nice. So you know you're not out of the square root yet. So let's see, what was it again? 25, there it is. Times 0.8375 divided by 80. So that's the error I get. Almost 11% error. The standard error we normally see on polls and such is like 4%. Can anybody figure out why this error is so big compared to that? Yeah, two things. One is I want to be 99% confident. I'm going to have to go further out than normal. A second thing is, what always makes us trust what we see less when we take a sample that is smaller? And 80 is not a very big sample. I don't know if you guys see that. Okay. The bigger the sample, the smaller this is, the smaller the error is. So we got an error of 0.1062, like a little, almost 11% error. So now if you add and subtract that, what do we get? Here we get 0.0563, is that right? Yeah. Up to 0.2687.
Did you already put the 0.162?
Yeah, so that's this minus this is here,
Right.
and this plus this is there.
Right.
All right. So you always make sure you can get to this point where you actually constructed the interval, and then the sentence we write is interpreting that interval. What does it mean? So what sentence would I write here? We are 99% confident that the interval. Now, the last problem we did was test grade, so there wasn't any real units to put, but you always got to put units when there are units. When you have a percentage problem, the units are the percentage. So convert those to percentage. We are 99% confident that the interval 5.63% to 26.87% contains the true percentage of people that do what? Like coffee, ice cream. I don't like coffee ice cream. That's why I made the percentage smaller. I like coffee. Just give me coffee. Some of you guys might not even know coffee ice cream exists. I don't know. I don't even know if it still does, to be honest. I never looked for it. All right. So, you guys try number 1 out on this handout. And then number 2, we got to talk about it. You can look at it if you want to.